Guys, coming at you with an enticing video about math, and we're continuing the series in geometric proofs. This is a series covering the vocabulary words that you commonly see in geometric proofs. Please keep in mind that geometric proofs are very difficult for some students and sometimes take quite a while to get right, but it's an important life skill, if you ask my opinion. I think that thinking logically and backing up your argument is an important skill that is sorely lacking in this world. This case here, we're going to be talking about alternate interior angles in geometric proofs. So first we're going to talk about congruency. We're going to talk about how we prove triangles are congruent. Then we're going to look at the definition of alternate interior angles. And then we're going to do two proofs involving alternate interior angles. So let's take a look. Okay, first, the definition of congruency. Congruency is a physical concept in geometry where we're saying that everything is exactly the same. All the parts of a shape are congruent or are the same to another shape if both shapes are the same. And it's different than a numerical value of equivalence, so we're not saying 5 equals 5 here. We're saying that this triangle monster is exactly the same as this triangle monster, and we have to prove that through logical thinking. Okay, let's take a look at how we prove triangles are congruent. So we have these 5 methods here. We have side, 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 which uses 3 pairs of sides to prove that these two triangles are congruent. So when these 3 sides are the same, the triangles are the same. We use side angle side to prove the triangles are the same. So when we have a pair of sides and then an angle in the middle or included, I can make the statement that these triangles are congruent. We have angle side angle. I could use that form of congruency as a statement to prove these triangles are the same when I have 2 pairs of angles and then a pair of sides included or in the middle. I have angle, angle, side, which is a way to prove these 2 triangles are congruent when I have 2 pairs of angles, then a pair of sides that are not included or not in the middle. That's the difference between these two. Then we have hypotenuse leg, which can only be used or is only useful for right triangles. So when I know I have a right triangle, I could say the hypotenuse, which is opposite the right angle, and any leg, if they're congruent, I could say the triangles are congruent by hypotenuse leg. Okay, let's take a look at the definition of alternate interior angles. So it's a little bit of a complex definition. Hopefully the picture that was drawn for you clears it up. So alternate interior angles are angles that are formed inside 2 parallel lines on opposite sides of a transversal. So in other words, angles that are opposite each other and inside parallel lines. That's what alternate interior angles means. So here I got my 2 butterflies. Those are alternate interior angles inside the parallel lines. Then I got the 2 smiley faces. Those are alternate interior angles. Again, inside the parallel lines. Alternate exterior angles do exist, and those would be these angles out here. Okay, let's take a look at 2 proofs. So this is a common proof we see that involves triangles and alternate interior angles. So let's see what we got here. It states here that GF is parallel to BH. And it tells me that DF is congruent to CE. So I wrote the givens down, I copied them down. Those arrows indicate that these lines are parallel. And I have that DF is congruent to CE. Okay, so thinking this through, right, what we have to be careful here is I also have these triangles out here. But these triangles are not useful. I only need to worry about these guys. And in fact, if I look at what I need to prove, it says DC and FE. These two lines is what I need. So I need these two lines here. These triangles out here are not useful to me. So I could actually just concern myself with this part. So now what I see is I have alternate interior angles. I have alternate interior angles because these lines are parallel. Alright, so I have to look at to see which ones are useful to me. So if I cover this up, I see that just these two angles are useful. Yes, I have alternate interior angles here and here as well. But these are not useful because I'm not going to use those triangles in my proof. I'm just going to use these two. Then I have the reflexive side here. Okay, so let's write that up. So first I'm going to get the reflexive side out of the way. So I'm going to say that DE is congruent to DE. You could also flip this if you like and say DE is congruent to ED. It's up to you. And that's because of the reflexive property. Okay, now I'm going to address these alternate interior angles. So here, I'm going to say that angle CED is congruent to angle FDE. Whoops, let's get that angle side in there. Angle FDE. When labeling these angles, make sure that the vertex, which is what I'm pointing at, that letter is in the center of your three letters. Then you kind of go out from there. So I'm saying this angle and that angle are congruent. And the reason why they're congruent is because they are alternate interior angles. And I can make that statement because I know that GF is parallel to BH. So alternate interior angles. Okay. Now I have my alternate interior angles. I have pair of congruent sides. I have a pair of congruent angles included. And then I have a reflexive side. So I can say that this triangle is congruent because these triangles are congruent because of side angle side. So I'm going to say that triangle CDE is congruent to triangle FDE because of side angle side. Now I'm not done yet. Here it says prove that DC is congruent to EF. Well, I have to say, since I have my triangles are the same, I can now say the parts of the triangles are the same. So I can make the statement that this and this are the same because the two triangles are the same. And that's what I'm going to say. It's often referred to as CPCTC. You can reference another video for that. So I could say DC is congruent to FE because of CPCTC. Okay? And that's that proof. A very common proof involving alternate interior angles. Okay, next. Here's this one. This is another common proof. Now, in this proof, I'm just going to point out, so we don't get caught up in labeling all the angles, I'm going to number them. You have the power to do that in a proof if you want to, if it's freehand, if it's not multiple choice. You can just number the angles. Okay. So we want to prove that this is a parallelogram. The definition of a parallelogram is that opposite sides are parallel. So I know that AB and CD are parallel. Now I have to prove that BD and AC are parallel. This can be a complex proof, so we have to be careful here. All right, let's take a look at the given. So the given states that AB and CD are parallel. It also states that AB and DC are congruent. So let's mark that off. So I have AB is congruent to DC. And also I have the parallel lines. So the way alternate interior angles are going to work here is they have to touch the lines that are parallel. So angle 3 touches that parallel line, and angle 2 touches that parallel line. Okay, so that's how I know those are my alternate interior angles I'm going to be working with there. Now I'm also going to have that reflexive side here again. Okay, so I can state that the triangles are congruent by side angle side again. So let's do that. Okay, let's get the reflexive side out of the way first. So I'm going to say BC is congruent to CB. And that's the reflexive property. Okay. Then I'm going to make the statement that angle 2 is congruent to angle 3. And that's because they're alternate interior angles. I can make that statement because of this given alternate interior angles. Okay. Now I can make the statement that the triangles are congruent. I can say that ABC is congruent to DCB because of side angle side. So I've established side angle side congruency here. It's congruent to DCB because of side angle side. Okay, I'm not done yet. We want to be done, but it's not the case. So here what we have is we have to prove that ABCD is a parallelogram. Most proofs we stop here, but this one's like the villain that keeps coming back. So we have to have a whole nother half of the proof here. So let's take a look. I'm going to use the fact that I proved these triangles are congruent in my favor. So before, and this might be a little bit long-winded, and I apologize ahead of time, right? Before, because I knew that AB is parallel to DC, they gave that to us, I could state that angle 3 and 2 are congruent as alternate interior angles, because alternate interior angles, by definition, exist in parallel lines. Well, I can work that backwards. I could say if I have alternate interior angles, then that means I'm going to have parallel lines. And in a parallelogram, I need to prove that these sides are also parallel. Well, what I'm going to do is I'm going to make the statement now that angle 1 and angle 4 are congruent. And I can make that statement because of this. So I can say that angle 4 and angle 1 are congruent because these triangles are congruent. So I'm going to say here angle 1 is congruent to angle 4 because of CPCTC. So CPCTC. Or I'm saying angle 1 and angle 4 are congruent because the triangles are congruent. Or they're the same. They have to be because the triangles are the same. So now I can state from there that AC is parallel to BD. I can say that this is parallel because I have the alternate interior angles that exist in there. So I'm going to say that AC is parallel to BD because angle 1 and angle 4 are alternate interior angles. Okay, let's get that written out. That's an O. angles. Okay. Now, so now that I've made that statement, right, I have the opposite sides are parallel. So I have AB is parallel to CD, which was given to me, and I have AC is parallel to BD, which is something I proved. So now I can make the statement that ABCD is a parallelogram can fit that in there, okay, is a parallelogram because opposite sides are parallel. I could say, let's see, there's a number of ways I can make this statement. I could say that AB is parallel to DC and AC is parallel to BD. That's one method. I could say because of the properties of a parallelogram, I could say that opposite sides are parallel and just keep it simple like that. So it's entirely up to you at that point as long as you're using the facts behind in your favor. And one other thing I kind of like to point out here we are again, we made a statement, we used that statement to make a fact, we made a statement, we used that statement to make another fact, then we use that statement to make another fact, then I use that statement to make another fact. And that's the logic of geometric proofs, okay? It's repetitive logic, cyclic logic that's very difficult to undo. That's why they call it proving. Okay, guys, I hope you guys found this video in geometric proofs using alternate interior angles helpful.